Hysteresis in rubber. What is it and why it matters? Welcome back, my rubber hearts. Today we are diving into a topic that lies at the heart of rubber science and has a massive impact on how rubber performs in real-world applications. Hysteresis. If you've ever wondered why some tires save fuel while others grip better on the wet roads, or why certain rubber parts absorb vibrations better than others, the answer lies in hysteresis. It's a fascinating and complex subject, but don't worry, I'm here to break it down for you in a clear and engaging way. Let's start with the basics. What is hysteresis? It is not an inherent property of rubber like hardness or elasticity. Instead, it's a behavioral response that occurs when rubber is subjected to repeated deformation, like stretching, compressing, bending, or twisting. In simple terms, hysteresis is the energy lost during these cycles. When you deform rubber, you put energy into it, but when it recovers or relaxes, not all of that energy is returned. The portion of energy that is lost is converted into heat, and this phenomenon is what we call hysteresis. It's a direct result of rubber's viscoelastic nature, which means it behaves like both an elastic solid and a viscous liquid. Understanding hysteresis is crucial for anyone working with rubber because it influences how rubber performs in dynamic applications. Take tires, for example. A tire rolling along the road constantly deforms as it contacts the surface, and each of these deformations generates hysteresis. The energy lost as heat contributes to something called rolling resistance, which directly affects fuel efficiency. The lower the hysteresis, the less energy is lost and the better fuel economy. On the other hand, in applications like vibration isolators or shock absorbers, high hysteresis is actually desirable because it allows the rubber to dissipate vibrational energy, reducing noise and preventing vibrations from transferring to sensitive components. Now that we know what hysteresis is, let's dig a little deeper into the science. Rubber's behavior during deformation is influenced by viscoelasticity, which is a combination of two opposing forces. The elastic part stores energy and allows the rubber to snap back to its original shape, while the viscous part dissipates energy as heat due to internal molecular friction. When you stretch or compress rubber, these two forces compete, and the result is a lag between the applied stress and the resulting strain. This lag is what creates the energy loss we see as hysteresis. If you were to graph this process, you would see a loop called the hysteresis loop on a stress-strain curve. The loop is formed because the path of loading, when the rubber is deformed, and unloading, when it returns to its original shape, are not the same. The area inside the loop represents the energy lost during one cycle. The larger the loop, the more energy is lost and the greater the hysteresis. So, how do we measure hysteresis? The most common method is using a dynamic mechanical analyzer, or DMA. This instrument measures the viscoelastic properties of rubber, including something called the damping factor, or tan delta. Tan delta is the ratio of energy lost, which is viscous behavior, to energy stored, which is elastic behavior. A higher tangent delta means higher hysteresis. Another way to assess hysteresis is through cyclic stress strain testing, where rubber is repeatedly deformed and the energy loss is calculated from the hysteresis loop. In tires, hysteresis is often measured indirectly by evaluating rolling resistance. Now, why does hysteresis vary between different types of rubber? It all comes down to polymer structure. Flexible, low glass transition temperature polymers like NR or EPDM have low hysteresis because their chains move easily and recover energy efficiently. In contrast, polymers like SBR or CR have higher hysteresis due to rigid molecular structures or polar groups that create more internal friction. Fillers also play a big role. Carbon black tends to increase hysteresis because of its strong interactions with polymer chains, while treated silica with coupling agents can reduce hysteresis, making it a popular choice for low rolling resistance tires. Cross-linking density is another critical factor. High cross-link density restricts chain movement, reducing hysteresis, but too many crosslinks can make the rubber brittle. Temperature and deformation frequency also influence hysteresis. At higher temperatures, rubber behaves more viscously, increasing hysteresis. Similarly, rapid deformation cycles lead to higher energy loss due to faster molecular motion. Now, let's tie all this back to real-world applications. In tires, low hysteresis is essential for reducing rolling resistance and improving fuel efficiency, which is why tire manufacturers carefully select polymers and fillers to achieve this balance. However, low hysteresis isn't always the goal. For example, in wet or icy conditions, a tire needs higher hysteresis to maintain grip because the energy dissipation helps the tire cling to the road surface. In vibration isolators, high hysteresis materials like CR or HNBR are used to absorb and dissipate vibrational energy, protecting equipment and improving comfort. Rubber technologists leverage this understanding of hysteresis to design compounds tailored to specific applications. By selecting the right polymers, fillers, and additives, and optimizing the cross-linking density, they can fine-tune the material's performance. For example, a conveyor belt might need low hysteresis to reduce energy consumption, while a protective mat might require high hysteresis for protective shock absorption. To simplify this for everyone, imagine hysteresis like a sponge. When you press a sponge, it absorbs energy. A low hysteresis sponge quickly springs back, releasing most of the energy that you gave it. A high hysteresis sponge feels slower and softer, absorbing more energy as heat. Rubber behaves similarly, and understanding how to control this behavior allows us to create materials for a wide range of purposes. So, hysteresis isn't just an abstract scientific concept. It's a vital factor in the real-world performance of rubber. Whether you are designing a tire, a seal, or a vibration isolator, understanding and managing hysteresis is key to achieve the desired balance of efficiency, durability, and functionality. Thank you for joining me in this deep dive into rubber hysteresis. If you found this episode helpful, don't forget to like, share, and subscribe to my Rubber Heart. Let me know in the comments if there are other topics you would like me to cover. Until next time, stay curious and stay bouncy.